All right, so we're done with chapter 20 and we're moving into chapter 21. And for those of you guys who love carbonyls, I've got good news. We've got more carbonyl stuff. So anyway, if you remember way back in the day, almost like 3 days ago, when we were starting out chapter 20, we said that we would be in carbonyl chemistry for quite a bit. The point that I made then was that carbonyls are pretty diverse in what they can do, and they're extremely powerful functional groups that can do a lot of chemistry, right? Now, chapter 20 dealt with how it can react the carbonyl itself, right? How we can make ketones and aldehydes and all these derivatives of the acids. And now what we're going to do is we're going to move one carbon over to what we call the alpha position, okay? And then we're going to really change things up and move to the beta position later on, okay? But we'll get to there when we get to there, okay? So first things first, what we got to talk about, or what one of the big concepts, is that the carbon, the positions there in the blue and in the green are, we would call those the alpha positions to the carbonyl, right? So we would call those the alpha carbons, and alpha carbons have alpha hydrogens bound to them, right? So they are the positions that are next door to the carbonyl. Now, why we care about those is actually those are fairly acidic hydrogens. I should have probably looked this up, or at least put it into my brain a little bit earlier. I think they quote you guys a pKa in here somewhere about those. Oh yeah, there it is, okay. So the pKa of those are about anywhere from 16 to 19, right? So about 16 to 19, oh, I'm sorry, I should give you guys the page since I was just looking it up. On page 960, so 960. So on page 960, they kind of give you the pKas. Now, I don't care if you guys memorize the pKas. What I'm telling you is that the pKas for these are about anywhere from 16 to 19. I know, I can hear you guys already texting your friends like, oh my gosh, this alpha hydrogen is 16, right? Let's put this into context, right? So ignoring the carbonyl for a minute, right? It's basically, we're just talking about an alkyl group, right? And if you remember back when we were learning about alkanes, right, the pK of an alkane is like in the 40s. So now, in some of these cases, we have pKas that are like 16. That is massive, right? That is a massive change on pKa, right? And if you think about it, like, wait a minute, I think there's another common group that we use that has a pKa around 16. That's right, it's our alcohols and waters and all this kind of, right? So we have a pKa that's similar to water, essentially, is what it can be in some cases, right? And that's pretty darn fantastic. And it also opens up the realm of chemistry that we're going to deal with, because those hydrogens are acidic. Or really, we can just back up and say because they're more reactive than alkane hydrogens, right? We can actually start to do some chemistry with them, right? And we can, the first thing I'm going to learn is alpha halogenation. So we're going to learn how to put a halogen group on those alpha positions. But before we got to get to that, we got to learn the mechanism for this chapter. And the mechanism for this chapter is on enols and enolates, okay? So that's going to be the core idea that's at play behind all of this. Establishing an equilibrium, I guess we could say that, right? Establishing an equilibrium wherein we have an enol or an enolate, okay? Now let's learn this. It's pretty darn easy, okay? And we're going to do something really weird. We're going to put a carbonyl under acidic species, under acidic conditions. Shocking, I know you guys are shocked, right? So remember we talked about this a lot, and what is an acid and where it gets attacked, blah, 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 right? All that kind of stuff. So let's see what happens here, okay? So we've got some kind of acid, we'll just shorthand it as H+, even though I don't like doing that, but I don't know, I'm feeling kind of lazy today, so pardon my laziness, okay? So we protonate the carbonyl, oxygen, and, okay, what can happen is this. Got it? Interesting. So now essentially we have a double bond here, and this carbon here becomes a little bit more reactive, right? Because if we think about it, right? If we think about it, right, we now have a double bond there. Now, how much chemistry have we done with double bonds? The answer is a lot, right? Like, well, what kind of chemistry? How do we know that it's reactive? Well, let's think about this for just a second then, right? Let's do something crazy and do this, okay? Now, practically, this is something that's really going to exist to a large amount of solution now, right? Negatives under acidic conditions, not too great. But take a look. The point being, now we've got a negative at that alpha position. Of course, that already makes sense, doesn't it? Right? Doesn't that already make sense? Right? Because, okay, we took away an acidic hydrogen, right? When you pluck away an H+, we leave behind a minus. Okay? Now, under acidic conditions, obviously, this isn't going to exist all that much. But that's the idea behind it. Now, we can do the exact same and really change things up and put it under basic conditions. Okay? And I think you guys can see where this is going to go. All right, we got some water around. Whoops, let me draw my hydrogen here. Okay, so we got this, 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 and then we can just kind of polish things up a bit here. Okay, cool. And you see how, in essence, we end up at essentially the same position here, right? That's all we're really talking about. Now, these, for most enols and enolates, they are the lesser species in equilibrium. By far, right, in most of the cases, right, we'll talk about some exceptions and things, by far most of the time we're going to exist as the ketone or in the ketone species here, okay? There are some exceptions to this also. As we play with the electronics, as we use different bases, right, we can start to favor the enolate form here more, right? But it's this idea, right? It's this idea that under acidic or basic conditions, we can basically put a negative charge onto that carbon right there at the alpha position, okay? And that's going to be a relatively weak negative charge, right? For a couple of reasons. It's delocalized and all this other kind of stuff, right? It's going to be a relatively weak, which makes it a decent nucleophile, and so we can start to add things at that alpha position. That is the key right there, right? The key right there is that this isn't a full negative charge localized on a carbon, all right? Now, good practice would be, how do we get back to our starting material here, right? Under basic conditions, how can we go from here back to here? Remember, if we're establishing an equilibrium, we should be able to draw the forward and the reverse mechanism for that. And the same thing under acidic conditions, okay? So see if you guys can go through and do that. And if not, drop me an email and we can work through it, okay? All right, so let's learn the first thing that we can do then, all right? So the first thing that we want to learn is how to kind of favor these things using a different base, okay? So here we go to the idea that if we use our buddy NaOH and H2O, right? In essence, what we'll have in solution is a mixture of our starting material and some of our enolate here, okay? So we'll just have a little bit of both. The exact amount and the percentages is going to change depending on some stuff, but the point being, we will just have both of those present, okay? Now that might be useful. In fact, we're going to come back and use this to our advantage in a little bit, okay? So I don't want to give the impression that this is necessarily something negative, right? If we change bases to our good old buddy LDA, okay? Now, what is LDA? Now, LDA is our lithium diisopropyl amide, right? We talked about this a little bit. All right, there's our buddy minus the lithium, right? But there's diisopropyl amide, right? Diisopropyl amide, an extremely powerful base. Now watch, if it's an extremely powerful base, it's going to act like a base, and it's going to want to grab one of those alpha hydrogens. Powerful bases make weak acids. And equilibrium always favors the weaker acid, right? And that would be a great argument to have as to why that is, and you might have to go back and recall your Gen Chem stuff, right? But if we pick a really, really powerful base, this is far more powerful than sodium hydroxide is, right? And it's also a bulky base, which is important too, right? Because remember, let me take a quick aside here, right? We are going to be talking about reactivity here. That doesn't mean magically the reactivity at that carbonyl carbon suddenly disappears, right? So if we had an unhindered base, we'd have some competition where the carbonyl carbon gets attacked, right? So having a bulky, strong base there is going to be extremely important, okay? So if we do that, then really all we have in solution after we let things kind of settle is our enolate, okay? And that's going to be important too. Cool. So let's work off of this idea here then, right? Let's work off of having a strong base or a decent aqueous acid, and let's see what we can do with it, okay? First reaction we want to learn is kind of where we start everything with chemistry, it seems, and organic at least, is how to add a halogen. So we can add a halogen under acidic conditions. Okay. So under acidic conditions, this will be our major product. Cool. Can you guys think of what the mechanism is? Right? Remember, we have an acid that's typically always going to be used in the first step of a mechanism. Okay? So let's make the enol. Okay? We'll bring everything down here. Okay, we got this, that, right? Now let's set up our enol. Okay. So remember now what we see when we see an enol, right, an alkene with an enol. What we really think is that carbon right there has a negative charge on it. It's got a negative density on it. So if I bring something like bromine around, remember bromine has pretty strong dipoles, right? The dispersion forces, right? It can have positives and negatives exist on it for spontaneously, right? So dispersion forces, London forces, van der Waals forces, all that kind of stuff. So now we're going to make our negative attack our positive. So let's do that. So we are going to follow that set of arrows. Okay. And then something's going to come in and clean that up. Let's bring in some water, I guess. That seems like a very good choice since it's our solvent. And then we can get to our product here, right? Cool. So this is going to be kind of the name of the game. Make our enol and then have it do something, right? Make our negative and then have it find something positive. Now the good news with this is now we've got a halogen there, and we can do a lot of chemistry with halogens, right? We really can. The second thing is that under acidic conditions, we typically will only see one bromine added, okay? And they talk about that bit, a bit when they get to this part of the chapter there, right? So we really only tend to see one of our halogens added. That is opposed to us doing the same thing under basic conditions. Okay. So under basic conditions, what we can end up doing is adding multiple halogens there. Okay. So what's going to be our mechanism in this case? Well, right. First thing we got to do is basically set up the enolate, right? And we could draw the resonance structure there if we wanted to. Right? And then we can have the same thing happen, right? And that's good stuff, right? Cool. The thing is, right, now this hydrogen here is actually going to be even more acidic, right? It's going to be even more acidic to the point that our base is going to come back in and deprotonate that position again. Okay, so we're going to end up adding another bromine there. We really can't stop adding multiple halogens to those alpha positions, okay? So this would come back and do this exact same thing again, where our product in this case would likely be something like this. Okay, and even we might add the stuff to the other side there also, right? But I think you guys get the point, right? Alpha positions are going to get halogenated. Now we can actually use this to our advantage, okay? We can actually use this to our advantage. Watch what we can do, right? So let's take this compound instead, right? NaOH and a bunch of Br2, right? When I do this, here's my product. I make a carboxyl 8. Ooh. And I end up making CHBr3. And this is bromo form, right? And we can also do the same reaction with iodine, and we would make iodo form, right? And in fact, it's a very common lab for organic where we do the iodoform test. Because this is, you'll see a nice, pretty yellow solid precipitate out of reaction. Because iodoform is a nice white, yellow solid, right? But so this is called the iodoform or bromoform reaction. And what it'll do, it'll end up taking methyl groups next to carbonyls and basically chewing them off and spit off bromoform or iodoform. What would the mechanism be for this? Why does this work? Why does this work? A very good question, and I want you guys to figure it out. I know, I'm not going to give you the answer right here. But this is useful for us. Why? Because we can take a methyl group and turn it into a carboxyl 8, and then, okay, let me move this stuff out of the way. Right, and then, if we came back in and acidified, whoops, not just H3+, right? We could turn this into a carboxylic acid. And we can do a lot of chemistry now with carboxylic acids also, okay? So notice what I have on the other side. The other side here, I've got a quaternary carbon. There's no hydrogens there, okay? So this isn't going to get deprotonated. It's not going to get reacted at all, right? So only where we have alpha hydrogens are these things going to get reacted, okay? Please, please, please go and figure out why this reaction works. I know you guys have the answer, okay? I know you guys know what you're going to have to use stuff from chapter 20 and then what we just learned in chapter 21 to try and figure this out. Open the door and close the door, right? How does the opening and closing the door work, though? Okay? But there you go, that's the first part, a nice kind of short video here to kind of change things up. The next video we're going to talk about one of the bigger parts of this, and that's going to be the aldol condensation stuff. Okay? But that's it for now, and I will see you guys in the next video.